Bismillahirrahmanirrahim. Today we will discuss transformation laws for Cartesian components of vectors and Cartesian components of tensors with some examples. So let us start. Let us consider any vector A. Then we can write components of this vector A with respect to basis EI, and this is given in equation 1. AI equals to A dot EI. That if you have simple vector A, then if you want to get its first component, then you will have to take dot product of this vector A with E1. So you can write it AI equals to A dot EI. AI is the nth component of vector A. Now equation 1 is with respect to basis EI. Now when you will write components of this vector A with respect to basis EI dash, then you can have equation 2. Simply from equation 1 we can write AI dash equals to A dot EI dash. There is no dash at vector A because vector is same in equation 1 and equation 2, only we are changing bases. In equation 1 bases are EI, and in equation 2 bases are EI dash. So basically we want to calculate a transformation law which transforms components of vector A in basis EI to the components of vector A with respect to basis EI dash. That how we can relate these two components. These two components mean with respect to different bases. So we know that EI dash equals to QMI that our bases are related with this equation EI dash equals to QMI. This is given in your previous lecture. So what are QMI? QMI are simply the components of transformation matrix. The matrix which transforms your basis unprimed to basis primed. Then simply use this EI dash into equation number 2. Then equation number 2 will be written as AI dash equals to A dot and EI dash will be QMI. Now as this QMI are simple scalar numbers, so we can write this outside. Then we have AI dash simply equal to QMI A dot EM. So this A dot EM is the mth component of vector A, which is equation number 3. So this equation number 3 is basically the required transformation law. You can see that this is transforming components of vector A with respect to basis EI to the components of vector A with respect to basis EI dash. That now here M is dummy and I is free index. So we know that I is varying from 1 to 3, that A1 dash, A2 dash and A3 dash. So A1 dash will be equal to QM1 AM, and simply you can write Q11 A1 plus Q21 A2 plus Q31 A3. Similarly you can have second equation E2 dash, then third equation E3 dash, then then you can write its matrix form in this way: a1 dash a2 dash a3 and equal to this simply. So this can be written matrix A dash, this is transpose of Q, this is matrix A. Here you have to note one thing, that difference between this and this. These two are the matrices of the same vector A. This is the matrix of vector A with respect to basis ei dash, and this is the matrix of same vector A with respect to basis ei. So if we have this, it means that this is the matrix of transformed vector of A through Qt. Matrix of Qt. So difference between this and this is that this is the matrix of vector A with respect to basis ei dash, and this is the matrix of transformed vector of A through Qt. This thing is similar to this. I should write it that matrix of a Q and T should be outside of this bracket. I have made a mistake here, so please correct it. No, you can move back from dash to undash. So from equation number 4, if you will simply operate with matrix Q on both sides of 4, then you can have this equation. And we know that Q is orthogonal, then we have QQ transpose equal to identity. Use this here, then you will have identity into matrix A, again will be A. This is the left hand side of this equation. So we have A equals to QA prime, that you can move simply from dash to undash. So there is a little difference, that where we have transpose, here we have no transpose in equation number 5. So we can write this equation 5 into initial notation in this way: AI equals to QIM AI dash. So again here it will not be AI dash, it will be A dash M. Here not I, here will be M. Equation number 6. So let us do some example related to this. Suppose that you have vector A, and with respect to basis ei, its components are 2 0 0, and you can write it as simply A is equal to 2 e1. Now you are asked to find components of this vector A with respect to basis ei dash, and ei dash are given. That how we can obtain ei dash? That ei dash are obtained by a 90-degree counterclockwise rotation of ei about e3 axis. That we are taking rotation about x3 axis. This is simple, the geometry of the rotation. This is x1 axis, this is x2 axis, so E1 will be along x1, E2 along will be x2. So if you move with an angle of 90 degree, then your E1 will be parallel to x2, which is E1 dash, then E2 will be E2 dash here. Or x3 is the fixed axis. Now we are given that our theta is 90 degree, so simply you can write E1 dash equal to E2, E2 dash will be equal to minus E1, and E3 dash will be equal to E3. Now you know that your transformation E1 dash equals to cosine of angle between E1 and E1 dash, E1 plus cosine of angle between E1 dash and E2 outside E2 plus cosine of angle between E1 dash and E3 outside E3. So cosine of 90 will be 0 simply, and this is cosine of 0 is 1, because cosine of angle between E1 dash and E2 will be cosine of 90 minus theta, and as theta is 90, so cos theta is 1. Similarly, you can write E2 dash equals to minus E1 and E3 dash equals to E3. You can directly write your components of A with respect to basis E1 dash EI dash with the help of this. Given that A is equal to 2E1, we know that what is E1. E1 is equal to minus time E2 dash. 2 into minus E2 dash. So we can write A is equal to minus 2 E2 dash. This is the component of this is vector A with respect to basis EI. That is a linear combination of EI basis 2E1 plus 0 E2 plus 0 E3. Now this is the vector A with respect to basis EI dash, linear combination of 0 E1 minus 2 E2 dash, 0 E1 dash minus 2 E2 dash plus 0 E3 dash. Now if you want to calculate this result from your transformation law, then what you need, you have to write only this matrix Q from your these three equations. Simply 0 1 0 minus 1 0 0 0 0 1, A dash will be equal to transpose of Q A. Now you can write simply Q transpose here, simply A, then you have 0 minus 2 0. This would be written as A equals to minus 2 E2 dash, because this is with respect to dash basis. Now simply if you want to transform A through QT, then it would be Q transpose of Q A, you will have transpose Q A 0 minus 2 0 and A dash. No, this is will be A dash equals to minus 2 E2. There is simple difference. You can see that in example we are asked to find components of vector A with respect to basis EI dash. And what is your vector? Your vector A is equal to 2e1 and result is A is equal to minus 2e2 dash. Both vectors are same in this example, A and A. A equals to 2e1, and after solution we have A is equal to minus 2e2 dash. Vectors are same, A. But if you simply transform your vector A with this transformation matrix, then you have vector A dash equals to minus 2e2. Minus 2e2, A dash. A vector is 2e1, and after transformation you have A dash, which is minus 2e2. Let us see another example. If you have simple ei dash, and we can have these bases ei dash by our rotation of angle 30 degree counterclockwise about e3 axis. We have to find components of this vector with respect to ei dash. Now you have this simple matrix Q, then its transpose Q transpose this. Simply you have this formula. Simply you will compute this product and you have 2 0 0. So this would be A equals to 2e1 dash. This is the rotation geometry of the rotation, that e1 dash 30 degree and e2 dash is 30 degree. And you can see that your A is parallel when you have your A with respect to e1 dash, then it is simply with respect to ei dash, then it is simply parallel to e1 dash, that it will be simply somewhere here with magnitude 2. And your matrix, this vector is also has magnitude 2. It will also be somewhere here with respect to basis ei. So do a question. Sorry, in exercise question number 2b 18. No transformation law for Cartesian components of a tensor T. Now if you have tensor T, then its components with respect to basis ei will be written in this equation 1. Tij equals to ei dot tej. So with respect to basis ei dash, its components will be given in equation number 2. Simply T dash ij equals to ei dash dot tej dash. So there is no dash on T because T is same in equation 1 and equation 2. Keep in mind. So we have again this equation. Put this equation in equation number 2. We have ei dash qmiem dot T, and ej dash will be qnjen. So you cannot write m again because of dummy index, because m is dummy and you cannot write it as 4 times m m m and m, so you have to use another letter instead of m. So we have used here n. So this is, you can write, I have written here t is linear tensor, so it will be linear, so you can write this scalar outside. Again you can write here is this scalar qmi qnj em dot ten, and this will be equal to tmn, simply using question number 1. So this is the transformation law for the components of tensor T, that how can we write components of tensor T with respect to basis ei dash if components of tensor T is given with respect to basis ei. So in matrix form, equation number 3 will be as T dash equal this and this is simply dash, this is transpose, this is simply T, this is simply Q. Again, this matrix and this matrix are the matrix of same tensor T. What is difference? Difference is that this is with respect to basis ei and this is with respect to basis ei dash, but tensor is same. Now if you have simply, as we have previously, that T dash equals to this dash, if is here T dash inside the bracket, then this T and this dash T will be two different tensors. So if we operate Q from left side and transpose from the right side, then we have this equation. Now this is a identity, this is again identity, so you have T equals to Q dash T Q T. So we can write this into initial notation in this equation. Tij equals to Qim Q Jn T prime Mn. Then simply you can move from dash to and dash. Let us consider an example that this is the tensor T with respect to basis ei, and you have to find components of same tensor T with respect to basis ei dash, and ei dash can be obtained by rotating ei about e3 with the angle theta 90. So you can write here e1 dash equals to e2 dash minus e1 and e3 dash e3. This is equation number B and this is C. This equation is C from here. Te1 will be equal to 0 times e1 plus 1 times e2 plus 0 times e3. Te1, you have to write Te2 Te3, then you will have this complete equation C. So Q is given, this is formula Q transpose T again Q, and you multiply this, you will have again this 2 minus 1 0 minus 1 0 0 0 0 minus, simply in simple manner. Now T11 dash equals to 2, T12 dash minus 1, T21 dash minus 1, T22 dash 0, T33 dash 1, T13 dash, T23 dash, T31 dash, T32 dash, they all will be 0. So Te1 dash is T11 E1 dash plus T21 dash E2 dash plus T31 E3 dash. So here will be dash T11 dash T21 dash again T31 dash. I should write dash here. I have written dash. Here should also be dash. And this is coming from your equation number 2. Coming from equation number 2 means that you can have equation number 2 from this equation. I shall say equation 2 is from this equation. They both are related. You have done all this in general in your previous lectures, if you have remember. And what is your equation number 2? Tij dash equals to ei dash dot tej dash. So if you want to write T11 dash will be equal to E1 dash dot TE1 dash, which will be simply T11 dash E1 dash dot E1 dash 1 E2 dash dot E1 dash 0 E3 dash dot E3 dash dot E1 dash will be 0. Then T11 dash 2 and T21 dash is minus 1. So Te1 will be equal to 2E1 dash minus E2 dash. No, you have to write Te2 dash Te3 dash. No, you have to also find your equation number A. Equation number A contains 3 equations, 1, 2 and 3. From your equation number B and C, which are given B and C here, equation number 7. And do this exercise 2B19 and please go through this lecture, and if you have any question, any query, then we will discuss this tomorrow on 10 a.m. Thank you so much.